Okay, we've been looking at so far have been isotopes, and isotope is a way of describing a single nucleus. And hopefully, you got to see on the simulation that we looked at that some of these nuclei are stable and others are unstable. So again, what this looks like. So here I'm looking at neon 20, so it has 10 protons and 10 neutrons. And it turns out, according to this chart, that it's stable. And oh look, 90% of the neon that you find in nature is made up of this isotope, meaning that 9 out of 10 neons that you dig up are going to have 10 protons and 10 neutrons. It turns out if I add, I don't know, 2 neutrons to this, that most of the other 10%, so 9.25% of the remaining isotopes are neon 22, meaning that it has 10 protons and 12 neutrons that are associated with that. And it's stable. If we add another neutron, this is now we're going to call radioactive and becomes unstable. And the challenge with the simulation is that nothing's stationary ever in chemistry or in nature. So let me show you a slightly different view. It's kind of showing the same thing, but a little bit more realistic. So let me see, go here. So here's an example. This is showing, in this case, lead. And the nucleus is protons and neutrons. They're not really red and gray balls of stuff. They're more complex. They're made up of quarks and components that have distant interactions. But what is realistic is that they're constantly moving and shuffling around. So this is what a nucleus is, more realistic view of what a nucleus looks like. So if I take something that's unstable, like polonium-211, and I wait long enough, eventually it's going to break apart. And this is what radioactivity is. Radioactivity is stuff like breaking apart spontaneously. And sometimes it happens more quickly than others, and we'll get into that. It's sort of interesting why. But we can make a prediction by knowing that if something's unstable, that eventually it's going to fall apart until it reaches something that is stable. So one way of representing this is zone of stability. So this is, here we go. So the zone of stability is just plotting on an XY axis, so the atomic mass, or a number of protons versus a number of neutrons, right? So they're taking every element. So element carbon's down here, it has 6 protons, and it's stable when it has 6 neutrons. So carbon-12 is very stable. It's also stable when it has 7 neutrons, so carbon-13 is also stable. But you notice some trends here. So this black line, this represents where the nuclei are stable. And generally, as you get to larger elements, you need a few more neutrons. Neutrons really is the glue that holds these things together. So protons, right, positive charge, they don't want to be next to each other. The likes repel. And the neutrons act there to glue it together using a strong nuclear force primarily. And that acts to hold them together. If I don't have enough neutrons, it's not going to hold together. But if I have too many, then it gets too big and is not holding it tightly enough and it falls apart. So this is one way of representing that and understanding that. So what we're going to get into, we'll get into what is an alpha decay, what is beta decay, what is gamma decay. So we'll describe those in some detail so you can see what happens when something falls apart. That's how we get nuclear fission. That's how we get the energy from nuclear power plants. But also you'll be able to make predictions. So notice here, so this blue area up here is indicating, well, if I have something that has this many protons and neutrons, it's unstable, and I can make a prediction what's going to happen to it. If I have something that's in this orange area, well, it's unstable, and I can make a prediction about what's going to happen to that. And so this is what we're going to be doing over the next period of time. Is we're going to be taking things such as this polonium-211 and figuring out what happens when it decays and turns into essentially another element and a radioactive particle. And this is taking a while. Where does it go? And then we'll get into the timing of these. We'll get into half-life and have a way of describing how quickly those things happen. So it happens more quickly for some things than others. And then finally, we'll get into uses of it. There it goes. We'll get into uses of that. And not only is it useful for the energy that's released, so both for nuclear bombs and for nuclear power plants, but it also is useful for figuring out how old things are. So we'll get into radio dating and using half-lives for that. Anyway, key thing is, so we're still looking at a single nucleus, and that single nucleus can be stable or unstable. If it's stable, nothing's going to happen. If it's unstable, that's what we're going to get into next, what happens when something's unstable and falls apart. Hope that helps. Talk to you soon. Bye.